Welcome to our second day of workshops. We will be getting started. Let's just see here. We do have quite a few people, 75 people so far, so great turnout. Thanks so much. I'm going to say good day instead of good morning or good afternoon because it really depends. We're everywhere in the world. So where I am, it's 9:01. So good morning to anybody on the East Coast here. So I'm going to get started. I'd like to introduce Emeli and Elena. They will be facilitating the workshop today. Emeli is the co-founder and CTO of Evidently AI, a startup developing tools to analyze and monitor the performance of machine learning models. And Elena co-founded an industrial AI startup and worked as a director of business development and marketing. Later on, she then directly worked with global metal and chemical companies to help them implement ML for production optimization as a CPO, where she led the development of the company's internal ML platform. So welcome, ladies. It's a pleasure to have you here, and we're so excited to get this up and running.
Thank you so much for this introduction. So let me start. As a matter of fact, we have been working with Emeli for quite many years, and right now we are together building a new startup, which is this open source tools for model monitoring, which we'll be showcasing right now. Today, Emeli will be hosting the workshop, and she will be showing a tutorial using an open Kaggle dataset. I will leave the links right now in the comments to the dataset and to the notebook, so you can follow them if you wish, or play later if you'd be interested. If you have any questions, please also put them in comments, and we will take them at the end of the tutorial. So now I will give the floor to Emeli.
Hi there. I'm happy to welcome everybody on this workshop. Elena, thank you so much for the links. I think it will be very helpful. So I'm going to start right now, and I'm going to start with a short presentation to discuss why should we care about monitoring of machine learning models, and then we will move to the demo straightforward. Let me share my screen. Hopefully you should see it right now.
Yes, we can see it.
Perfect. So just to start, I want to say that prior to working at Evidently, where we build tools to monitor and analyze machine learning models, I spent quite a lot of years helping companies build database products, build services on top of machine learning models. And on top of this experience, I'm going to discuss with you what can happen with machine learning models when we do not set up the proper monitoring, and why actually machine learning models can break in production, what can happen. So to start from, I need to say that in most cases when something is wrong with the model, it's because the input data is wrong. So in most cases, there are some issues with data quality and data integrity. It can happen because of many different reasons, like data processing issues, because we really rare use the raw data to fit into our machine learning models. In most cases, you have some data cleaning processes, we perform some feature engineering, and it's quite complicated pipelines sometimes. And if something is implemented incorrectly or we get some unexpected data, then we'll have some problems. It can be infrastructure updates from data sources. So if our pipeline breaks, in most cases, the model gives us incorrect output. In many cases, we use some external data sources to create features for our models. And in this case, if there is some changes in the upstream systems, or maybe changes in some external APIs, then we can also have some problems. For example, when CRM users decide to update the CRM schema or rename a couple of columns, or maybe add a couple of columns. In this case, if we are not prepared to such changes, our models can break. And the data loss also can happen. It can be the outcome of some incorrect implemented login systems, or even because of some physical problems where, for example, physical sensors just breaks. And in this case, we also lose data and sometimes get the wrong output of our machine learning models. But let's assume that data engineering team got their job done and we have no problems with data quality and data integrity. Even in this case, our machine learning models can break. And the second major thing that can happen with our model is data and concept drift, which I'm going to introduce to you like now. The concept drift is the case where the connection between the target function, which we are trying to estimate or predict, and features has changed. In many cases, it happens quite rare, but sometimes it happens very often. It happens because we use our model in the real world, not in vacuum. So real world has changed, the prices increase, the salaries hopefully also increase. And yeah, sometimes the connections between the data and the target has changed and we need to account to it. How to account? First of all, we need to figure out that something has changed. In most cases, we do it just looking into model performance, but we can analyze the target distributions and the features distributions. So we need to detect that something has changed, and we need to collect new data to be able to retrain our model. And from time to time, we need to retrain our model to keep the quality quite high. So this is how we work with the gradual concept drift. And one more type of concept drift is sudden. The recent pandemic is the perfect example of this. This is the case when almost overnight a lot of patterns has changed and our machine learning models are not relevant anymore. So in this case, I wouldn't say that we need to set up some specific monitoring because, right, it's really hard to miss such situation. But yeah, there is no standard way to treat it because, like, sometimes you can use, for example, expert knowledge to somehow post-process the model's output and somehow account to these new patterns. But in some cases, we need to rebuild the entire model or maybe come up with some another solution like rule-based system, or maybe something else to continue working in such a new case, right? So the data drift is the case where when our target function can stay the same, but the data distribution is changing. And this can happen due to many reasons. For example, if we are working on some client service and we suddenly ran new marketing campaign and we attract a lot of users from some specific channel, let's say social networks, and if during the training we didn't have a lot of example of users from this channel, then our machine learning model could have very few examples and didn't learn a lot of nice patterns related to this special group of users. And in this case, when we get more and more such users, our quality could drop, and we really need to retrain our model to demonstrate to the model these new users and help the model learn new patterns. So data drift can also affect model's quality quite well. So yeah, now we know that a lot of things can happen. The data quality and integrity issues, changes in the data. How we can account to it? Well, the simplest solution is to run the monitoring and see what is happening with the input data, with the features, and with the model. So I would say that machine learning based service is a service on the first place, right? So if we start to create monitoring system, we need to start from the service health, of course, because we need to monitor the memory, the uptime, the latency, and standard things that we monitor for any production service. But we just discussed that there are a lot of things related to the data, and we need to set up the additional layer related to models quality, the input data, the data drift, constant drift, and things like that. So before we move to the workshop, I just quickly mention what tools can we use to monitor our machine learning based services. And I would say if this service is not the first service for your company, you can just reuse the existing architecture. I mean, for example, if you use the Prometheus database to store your logs and calculate metrics, and Grafana to show the metrics and to setting up the alerts, then you can continue reuse the same infrastructure, but maybe, maybe you'll need to start logging more to add some specific events and additional metrics. but you can continue to use the same tools. And one more specific case, if you, for example, do not have any real-time system, or you're just starting to piloting your first machine learning-based service and it works in batch, then you can probably try to adapt some BI tools, like maybe Tableau or Looker, or even create some custom solution on Python with help of very nice libraries like Plotly or Matplotlib, or something that I'm going to demonstrate to you now. This will be a great start. In most cases, it's very lightweight and simple tools, and it's already will help you to see what is happening. For example, if you apply some analysis after each batch prior to set your predictions later on your business process, right? So such tools also can be very, very helpful. So how to start with the monitoring? I would say, like in all other tasks, it's very nice to be pragmatic there and take into account many different factors, like use case importance, complexity, and team resources, because of course, if you are limited in resources and you are even limited into your resources to build your database service, then of course you cannot like use twice more resources to create a very comprehensive monitoring system. So I suggest to take into account the importance of your use case and costs of the errors and risks, then the complexity of your service, because, well, batch is not the same as a real time, right? You can have different pipelines, more complicated or less complicated, and based on the infrastructure, decide how comprehensive the monitoring should be. And of course, team resources, because if, well, you work in a big IT company and you already have a very nice monitoring solution, then why not to reuse it? But if you're just starting, maybe it's good to start from something really simple to get used to it and to try different setups for your architecture. So, okay, now I'm going to move into demo, and for demonstrating how we can monitor and analyze machine learning models performance, I'm going to use back domain prediction dataset. It's a well-known dataset. I believe you already went through link and saw what is it, but this is the data where we need to predict the demand for bike rentals, and we have information for our predictions like weather, date time. We have information about temperature, humidity, wind speed. So based on this data, we need to predict how many bikes will be taken for a rental. So now let's move to our Python code and see what we can do. Yeah, I hope now you can see my Python. Should be like this. And today I'm going to demonstrate how we can use the package we are working on together with Elena. It calls Evidently, and it's open source. So you can, if you want, you can go to GitHub and see some examples and maybe try to apply it to your data. So first of all, I will import on the all the libraries I'm going to use today. It's some standard libraries like Pandas, NumPy, scikit-learn, datetime, and I also going to use the Evidently. So I import dashboard and some specific dashboard parts. I will we'll discuss it later, and profile is some specific profile. So here it is, and I have the data set stored locally, so I'm going to read it with help of pandas using function read C3. And the only interesting part here is that I'm going to parse dates here and use this date time as an index, because it's quite convenient to perform selecting on top of the date time. So that is why I use it as an index. And that's how my data look like. So this is the table where I have the time index and information like season, holiday, weather, temperature, wind speed, and amount of rented bikes. So first of all, we need to build machine learning model, and then we will have the object to analyze, right? And let us start from it. And I will mention there that I will skip the traditional part of really interesting feature engineering and bunch of experiments, because, well, of course, if we build the production-grade machine learning model, we need to start from data analysis, right? So we need to analyze the data distributions. We need to clean up our data set, check a couple of hypotheses about connections between different features, and target, then create the experiment plan, right? Try different models and different hyperparameter combinations, create good baseline and perform cross-validation based assessment of different models. So I'm going to just skip the whole interesting part, right? So I hope data scientists are not too much sad about it and just perform some very simple feature engineering. So we know that the demand is dependent on things like months, hour, weekdays. So let's extract this information from our date time. That's exactly what I'm going to do here, and add this information as the separate columns. So that's how it will be looking like, right? So I added 3 more columns. And now let's train the model. So my target will be count column. I will also have column prediction. So I just create the variable is this name here, and my numerical feature is temperature, feels like temperature, humidity, wind speed, hour, and weekday, and my categorical features are season, holiday, and working day. So this is the data I'm going to use to build my model. And one more maybe not obvious thing here, I will split my data into 2 parts. So first I call reference. This data I will be using for model training, and production to emulate the situation when we apply our model on the current data and see what is happening. So for reference, I will use only 4 weeks from the beginning of January till the 28th of January. And as a production data, I will take data for the next month, for February. So it's also 4 weeks. So let's select this data here. We are doing it with help of log command. So it's just part from our initial data frame, and it's just showing you that the structure is more or less the same, right? Exactly the same, I mean. So now let's pick the model, and as soon as we decided to not run a lot of experiments, the random forest ensemble is a safe choice, because you know that random forest is not tend to overfitting, right? So we can save some time on hyperparameter optimization and just select some reasonable number of trees, maybe even without limiting these trees into depth, because we know that random forest is not tend to overfitting again, and just use this model. So I perform my model training. I select numerical features and categorical features and train to predict the target column. So here it is. It's quite fast, right? Because we have only 50 estimators. And now I can perform prediction, and to make it a bit more comfortable, I will predict the target on top of my reference data and predict the target on top of my production data, save it, and we will work only with the final data frames. So let us run predict and add the prediction column to reference and to production data frames. So that's exactly what we are doing there. And now we have all set it up. We have our reference and production data frames that have pretty much the same structure. The only difference is that we used reference data to train our model, and the production data is new data that our model haven't seen before. So now we can analyze this data and see how our model performs. This is more or less the case when we trained our model on top of the historical data, put it into production, and start using this model into production and monitor what is happening. And let us assume that we have our information about our target function with some delay. For example, we have the updates only once a week. You won't believe, but sometimes this really is the case. And what we are going to do is to run our quality reports after each of the 4 weeks to see what is happening with the model, how quality changes, and why there are certain changes in the model's performance. But prior to that, let's perform some additional calculations. We are going to use evidently performance dashboard right now, and we need to somehow tell to our tool where in our data frame we have target function, where do we have prediction, where do we have numerical and categorical features. For doing this, I use column mapping. This is the standard Python dictionary. And I say that for target, I use the count. It's written in the target variable. For prediction, I use prediction name, right? And I have the list of numerical features and categorical features. I believe you remember we started from it. So it's here. And we just put this information into column mapping. And I need to say that having column mapping is not necessary. If you use the standard names like target, prediction, then tool will automatically detect where is your target and where is your prediction, and the splitting and all the features will be interpreted like numerical as soon as they have numerical data type, right? So, but here we are using column mapping to make sure the tool knows exactly where is target, predictions, and numerical and categorical features. So, okay, that's our column mapping. And first, what I'm going to do is to create the dashboard that will show us the regression performance. For doing this, I use the dashboard that we imported from Evidently. And there is only one parameter here. It's called tabs. This is the list, so we can have, for example, a couple of tabs here, but for now we are interested only in regression performance, so I put it there. And then I ran method calculate to calculate the dashboard, and I put my reference data here because first I need to figure out whether my model works well on the reference, because if it's not working well on the reference, then the whole rest analysis is not interesting actually, because well, model didn't learn anything on the data it sees, right? So let us run it on top of reference. So there is no production data. This is why I put none here, and column mapping. So then after my dashboard is generated, I can either run show command to see it in my Python Jupyter notebook, or I can run save command to create the separate HTML file that I can later open in browser or maybe send over to someone to analyze. But here I'm choosing to write show command, and here we are. There is our regression model performance report. First of all, it tells us that our target function is called count, right? And this is a short preview of quality metrics that was calculated on top of the data we had. So we can see that mean error is less than 1 byte, so that's quite well. It means that model learned all the patterns and predict pretty well on top of the reference data. Mean absolute error is also quite small, and mean absolute percentage error is quite normal. So let's analyze the visualizations, because we have a lot of very nice plots. For example, here we have predicted value versus actual value, and we can see that it looks like a diagonal cloud, right? Which means that the actual value and predicted value are quite similar. So we can zoom in, zoom out to see more closely how it looks like, but you can see that it looks pretty well. We also have the predicted versus actual in time, and we can see that on top of the training data set, model follows all the trends, right? So we can again zoom in somewhere and see that yes, model follows the trends pretty well, at least on the training data set. So let's move. We have different quality metrics visualized there. So this is the predicted minus actual, that's absolute percentage error. And we can see that our error is symmetric versus 0, right? So our absolute percentage error is in most cases quite low, but we have a lot of like high errors there. Sorry, browser issues. I have not very powerful laptop, so yeah, sometimes something like this is happening. So we also have error distribution here. We can see that it's symmetric, and we have the peak at 0 point. It's exactly what we expected, and we can see that our error is distributed normally, so which means that model more or less works well and not tends to underestimate or overestimate the demand for bikes. And we also have quite nice table at the very end with the visualization. So we know that when we work with regression model, it can either underestimate or overestimate our target function. So here we have the plot where we have top 5% overestimated objects and top 5% underestimated objects. But here you can see that it looks more or less normally, and there is no specific patterns or something like this that we can see. So that is why we are not really interested to analyze the error bias table, because we know that our model does not tend to underestimate or overestimate any specific segments of objects. So let's just skip this table for now, and maybe we will come back to it later on. So now we are sure that our model works well on the reference. Let's see what will happen after the first week of production usage of our model. So for doing this, we will take our production data frame, which calls production, and we will log the first week after training. So starting from 28th January, because we use for training only first 4 week of January, and ending at 7th of February, right? So we can reuse the same object, because we are going to build the regression performance dashboard again, but we just pass the new data and run method calculate to rebuild the same dashboard on top of new data. So it's done. Let's go show comments to see how it looks like. Sometimes it takes some time to show it, but here it is. So our first part of the dashboard is the same, because it's calculated on top of the reference data, and it's quite convenient because we can compare the performance of our regression model on top of the reference data set with the performance on top of the production data set. We call it current here. So this is the current data set with what we work, and we can see that there is some quality drop, which is perfectly okay, because, well, we expect some quality drop between a training data set and some external data set. And you can see that now our mean absolute error is equal to 15 bikes, which seems quite normal, right? Taking into account the average demand. But our mean absolute percentage error is much higher. So let's analyze how our predicted versus actual value looks like, and we can see difference quite straightforward, right? So on top of the training data, we have pretty diagonal cloud, and here on top of the current data, our cloud getting wider. So that means that sometimes we have much higher errors. But from the other point of view, we can see that it's still diagonal, right? So in most cases, our predictions are more or less okay. So let's continue analyzing the plots. There is the predicted versus actual in time, and we can see that our model still follows the trends, right? So it follows most of the peaks. Yes, there is something happening on the 6th February, right? So here we have the case where we underestimated the demand really highly, but on other dates it's more or less normal, and it looks like our errors start increasing with time, right? So maybe let's see. We also have error plots, and you can see that comparing to the reference, it looks like we start underestimating the demand a bit more often than we overestimated, right? You can see it on this plot because it's more often stays below 0, right? And you can also analyze others quality metrics. We can see the error distribution, and we can compare the error distribution on reference on the current data, and we can see that luckily we still have peak somewhere close to 0, but it looks like we starting the distribution started starts moving a bit to the left, right? So we really see that we are starting underestimate the demand more often. So let's check the normality. Yeah, you can see that there is some issues there, but years looks mostly normal, and you can looks what's happening there in our reference and prediction data per groups. And you can see, yes, there are some cases with our estimation and underestimation, but nothing too critical, let's say like this. Okay, let's move to another week. Second week, let's say that for our first week, our model worked more or less okay. The error, of course, increased, but nothing super critical has happened. So let's see how our model will perform for the next week after it went to production. So again, we can do the same easily. We just log the rows we need and perform the same estimation. So you can see that to build this nice informative report, we need only create dashboard object. We created it once at the very beginning, and then run calculate method with the data we have, like this. And after it, just run show or save command, depending on what is more convenient for us. So now we again run show command, and we can see that now our error getting a bit worse, right? So, but the patterns, the predicted versus actual cloud looks more or less normal. The model still follow the patterns, right? So looks like for the second week, it works more or less normally, right? So let's move there. We can see that our distribution unfortunately moves to the left again, but looks more or less normally. I will skip it for now because it has the same structure. We already analyzed it before. And let us add one more dashboard to consideration, which is the numerical target drift tab, because, well, we see that there is some pattern to, there might be some pattern to underestimating the target function. Let's see whether it is the case or not. So let's check, do we have the target drift or not? Target drift is the same as a concept drift. So for doing this, I create new dashboard object, and now I put the numerical target drift tab as a tab's argument there. And again, I run calculate command for the same data. So let's do this. It should be a bit faster because the dashboard is a bit smaller. So let me show it here, and let's see, do we have target drift or not, whether the target function start changing comparing to what we have on top of our reference data. So, and we can see that yes, the target drift is detected with some small p-value. So maybe we actually need to start worrying like right now, because you can see that the target function that we observing on our current data set is different from the target function we used to our training. I mean, it's not like two different target functions, but the distributions has changed. So this is the current data in red and reference data in gray. And you can, for example, see there that in the current data, you have much more cases with higher values that we even never observed during the training. So during the training, we have never seen any demand higher than 219 bytes, right? But in production, we have even like 256 bytes, right? And we know that random forest is not the best model for extrapolation, right? And maybe this is the root for our problems. But let's see. Let's see what we have there also. We have very nice plot with correlations, so we can compare the correlations between target function and features that we saw during the training and that we see during the production usage. Of course, correlation reflects only to linear dependencies between the data, right? But it can be a very nice proxy to see what is happening, because if the linear dependencies between features has changed, then probably non-linear dependencies or something else also can be changed, right? So this is a very nice proxy, and we can see that, well, there is some change in the correlation between target function and wind speed, right? So we can see it here, and some changes, maybe not that drastical, yes, between the temperature and target function. And that's just a visualization, another one visualization of target values. And we can see that, yes, sometimes we have like much higher values for target on our current data set. We also analyze the prediction drift there. So we compare distributions not only for target function, but to prediction, to the model output too, right? So we compare whether models output on reference differ from models output on the current data. I mean, we compare distributions, and what is interesting, there is no drift there. So we see that the target function has changed, right? There is drift there, but our model doesn't really reflect to these changes. So our model behaves like nothing has changed, right? So, and this might be the reason of the quality drop. And yeah, again, you have the same plots with correlation and prediction values. What is interesting, the prediction values hasn't changed, right? We even do not have that higher predictions, that high predictions that we have on top of our reference data, right? So that's quite interesting. And we have a table, target prediction behavior by feature. I suggest to skip it right now and analyze this table for the next week, because it will be much more interesting. So let's move to our last third week of production usage of the model. And let's again calculate the regression performance and target drift performance dashboard to see what is happening at the very end of the production usage of our model. So again, we run calculate command to the same object and then command show. Let's see, there are a lot of visualizations, so it takes some time. And let's see what's happening at the last week. So yeah, you can see that our mean absolute year and mean year is quite high. So let's analyze visualization. Yes, we can see that now we have some objects where we have pretty high mistakes. For example, like right there and right there. So let's see what's happening with our demand, and we can see that pretty much everywhere our model tends to underestimate the demand, right? It's easy to see it on top of every peak moments of demand. For example, let's zoom in there, and we can see that almost everywhere our predictions is lower than our actual values, so we almost always underestimate the demand. It's not a very nice trend. So yes, it's even easier to see it right here. This is the year predicted minus actual, and we can see that we are almost always below the zero. And we can analyze the distribution of year, and we can see that now it's even doesn't look like normal, right? We really tend to underestimate the demand. So now it's time to analyze the year bias table, because right there we can easily see, right, that our average year, mean year on top of 5% underestimated object is much, much higher. I mean, absolute value comparing to the year on the majority of object and top 5% of our estimation object. So we really tend to underestimate the demand. It can be easily seen there, or I can compare our 5% of object where we underestimate the demand on reference data and on current data, I mean training and production. And you can see that, yes, there is quite high difference. So let's see what can be the reason for it. And let's now analyze the year bias table. In this table, we analyzed the most common values or average values if you have numerical features for different segments of objects. So we see what was the most common or mean value for underestimate segment, majority segment, and our estimation segment, and see whether these values are different. And we order this table on top of the difference. And the first feature is a temp, it feels like temperature. Let's see what's happening. It's interactive table, so we can press on this button and see some visualization. And first visualization we have here is the distributions of the year on different segments of objects. Again, majority, underestimation, and overestimation. So I suggest to switch off the majority because it's not that interesting, right? And it's interactive plot, you can do it. And what you can see there, you can see that on top of our reference data set, there were no much difference on feature values, on feels like temperature values for underestimation and overestimation. So a model tends to underestimate and overestimate demand on the same feature space, right? But there we can see that this tends to overestimate our demand for lower temperature starting from 10 degrees to 20 degrees, and we tend to underestimate our demand for higher temperature. And this is the strong, I wouldn't say correlation, but strong signal, right? And it can help us to come up with some very nice hypotheses. For example, first hypothesis can be that temperature actually influences the demand highly, right? The second is probably our model hasn't seen the cases with high temperature during the training. The third is that our model doesn't really nice in terms of working with higher temperature. So maybe this is the cases, this is the issues with extrapolations and more. Of course, this is a really simple example because we intentionally train our model only on the first 4 weeks of January, where we haven't have a lot of warm days, right? So we did it to demonstrate how the model can break faster, right? But anyway, such visualizations are very helpful to figure out what is happening with our demand. And again, we can see this predicted versus actual value with respect to the value of temperature feature. And we can see that, well, there is a lot of examples with warmer days in the current data set, which model just haven't seen during the training, and this is more or less logical consequences that model doesn't really perform well with higher temperature. And we can perform the same analysis for other features. I believe for temperature we will have more or less same picture. Let's again switch off the majority, and yes, right, we can see that the picture is more or less the same. And I can continue looking at this interactive table and see what's happening, right? So let me quickly show the target drift. I believe it can be interesting. So should be ready right now. And yes, here we have target drift detected like 100%, right? I mean with 0 p-value. And you can easily see that there are a lot of, let me move it a bit, yeah. There are a lot of cases with high demand, which we can see in the current data set. And let's check the prediction drift. Prediction drift, again, not detected, right? So our model does not really account for the changes we can see. And the last question I wanted to bring up here is the data drift, because well, we know that data drift is something that does not really rely on having the feedback from our system. I mean, we can calculate data drift even without having ground truth, without knowing whether our model performs well or not, if we do not have the data for real demand. And from this point of view, data drift can be used as the early monitoring, right? As soon as we have the inputs data, as soon as we have features, we can calculate data drift and see what is happening with our data. So let us do this. I suggest us calculate, for example, data drift only for numerical features. And let's use our first week of production usage of the model from 29th of January to the 7th of February. And let's see how the data drift looks like. Again, I create the dashboard object. My tab is data drift. Then I run calculate, and then I run show. And that's the short table for data drift. And it's shows that we have 4 features drifted out of 6. And if we analyze what features are drifting, it's temperature, feels like temperature, humidity, and wind speed, right? So weekday and hour stay the same, likely. So which means that we can see that our weather is changing, and this is a very nice and strong signal for us to start thinking about seasonality if for some reason we didn't do it at the very beginning of the process, right? It might be that we just didn't have this data and we have no chances to work with this seasonality, right? But if we had, for example, data from previous year, that we might use it, we still can use it to retrain the model. So let's again open first column and see what we can, what is there. And we can see that we have the data drift plot where we have the mean value of this feature. It's mean temperature for current data and the expected values for this temperature. This one standard year from this mean value. And gray dots is temperature measured on top of the current data, and we can see that it starts filling out and it starts to getting warmer and warmer. And we can analyze the data distributions. So red is current, gray is reference, and we can see that, yeah, distributions are obviously different, right? So it shows that something is changing. And what else? I believe for other features, it will be more or less the same. Yeah, for feels like temperature, it changes even faster. So yeah, and you can see the distributions are really not the same, right? So we can see that current feels like temperature moving to the right, right? So it's getting warmer and warmer. So the data drift can help us to detect that something is changing even faster, and we could detect it even after the first week of production and update our model, maybe help our model to account for changing temperature, and maybe use models with better extrapolation quality. And I want to finally quickly touch the point about automatization of such thing, because during workshop, it's really nice to have dashboard, right? Because it's very visual. We can zoom in and zoom out to any visualization, analyze what is happening. But for real production usage, sometimes we prefer just to calculate things like p-value for statistical tests for data drift analysis, or value for different quality metrics for model performance analysis, put it somewhere like, for example, in Prometheus database, which I mentioned before, and then send an alarm from Grafana if some quality metric fall out from expected ranges, right? Or do something like this. And for doing that, of course, we prefer to have more simple format. And with help of Evidently, you can also calculate the GSOM profile. For example, here I want to calculate data drift profile for data drift. It will be the same data, but instead of dashboard, I create profile object. So my section is data drift profile section. Same data, same column mapping, same schema. First I create object, then I run method calculate. Here it is, even faster because no need to plot anything, right? And let me just show you right there how JSON looks like. I know that it's not something that we in most cases do in Jupyter Notebook, but why not just to see how it looks like? So here I have name of the profile. It's data drift, date time where we calculated this profile. So it's sometimes very useful if you put this data inside of some database. You have date time, you have name, and you have data where you have all the information about your data frames and calculated statistics. So some utility counts, categorical features we didn't have, numerical features, here we are, and calculated metrics. So for each feature have histogram calculated, so you could even like take the data for histogram and put it somewhere if you're interested, or if you want to show histogram in your visualization tool, you can just load it here. So histogram for reference data, and information about feature type, its numerical p-value is there, and that's it. So then we have the next feature. And JSON is a pretty common format to use it with some pipeline automation systems, with database, with monitoring, with other monitoring and visualization systems. So maybe for some of you it will be more convenient to use JSON, and if you got an alarm, then go back to Jupyter and create a lot of different dashboards to figure out what is happening with the model. So I believe that's pretty much it. That's all I wanted to share with you today. I want to thank you for your attention, and let's move to questions and answer session. I believe Elena should be still there.
I'm on standby, so we actually had quite a few questions. I believe some of them were asked in the middle, so they might have been answered, but let's just go one by one. And if you have any more questions, please put in the chat. So the first question is, if my data set is so big I can load it with pandas, is there integration of feature I can still use evidently?
It's a very nice question, and for me, it's for software engineers quite painful, because yes, I cannot say that evidently is the best scaling tool. It's not true for now, but we are working on it. There is only one scenario in which you can try to do it. You can calculate all the you can calculate HTML report and dashboards and JSONs from terminal. And for doing that, you need to have a CSV file, which is structured exactly as the pandas data frame. I mean, you should have their index or datetime if you have it in pandas features in columns. So pandas data frame, but in CSV format. For this, you can use terminal run of evidently. And now we are like in the middle of releasing sampling tool, sampling functionality. And for many of data sets, it really does make sense to use sampling, because, well, if you have, for example, a really high load service with a lot of users and a lot of data coming into your service, then you don't really need to have all your data to see that something is drifting. You can just have a sample and see all the relevant statistics. So my recommendation is try to work with terminal and just wait a bit for our next release. It will be with sampling. Great.
So next question is, nice plots. I would prefer different colors. Can we pass ours?
Unfortunately, right now, no. Only if you go directly to code, which is open source. So if you're interested, you can try. But honestly, I need to say that we didn't expect such interest to change in the color schema, and unfortunately, I do not have for now the config file for colors. I know it's weird and like it should be there, but we do not have it. We will add it a bit later, but yes, we will. Because now we're
growing pains.
For me to change colors, unfortunately, but we will do it.
So this is great work. The one challenge I see is that drift calculation requires batch data, say for the past week. Anything from evidently with respect to detecting drift on the fly, or do you simply recommend creating smaller windows in time, say 12 hours instead of 1 week? So how can we use it on the fly?
Yes, it's a very nice question, because it even doesn't matter what tool do you use. It's just statistically a nice question. So I believe the simplest way to solve it is to use a moving window, right? And really decrease the size of your window. And what I would do is I would take the historical data, the analyze data drift on top of your historical data with different window size, and see what seasonality you had, what cycles you had, and what is expected maybe a period of time on what you could have this data drift, and reuse the same window size for your real-time monitoring, if it makes sense.
So next question is, can you compare more than one model at a time, say side-by-side comparison?
Yes, you can perfectly do it. In this case, as a reference data, use the output for your first model, and as a production data output for your second model. Yeah, I know that the naming is not like makes sense in this case, yeah, but you can perfectly do it. The only limitation there is having the same structure of your data frames.
And so in this case, it would work for 2 models, but not more than 2 for the moment.
Yeah.
So is it built for discrete output also? I believe that's the classification performance report. We can
Yes, yes, it works. So it works for classification. It works for probabilistic classification when you have probabilities for object for being object of some target class, and it works for binary and multi-label classification, both with and without probabilities.
Mm-hmm. There are a few questions related to integration. So one is there a way to integrate this with Grafana? Another one is it possible to do the dashboard part in Power BI? And then the suggestions like Grafana and Tableau. So we've seen all these referenced.
Yeah, all these lovely tools. I also like Grafana and Tableau, actually. So for Grafana, it's a bit easier because, yes, if you use the profiles instead of dashboards, right, then it's JSON files, it's just text files. And yes, you can use some pipelines automation tool. You can even use Chrome, right, because you can, with help of Chrome, automate the run of evidently from terminal, if you like running things from terminal, and automatically generate profiles and use JSON as a source for Grafana. So this is something we expect people will do, and we are going to create some examples to cover it. For visual dashboards, no, unfortunately, so it's not possible to visualize it elsewhere instead of Jupyter Notebook or just browser. And for BI tools like Tableau, I'm not, I personally do not have a lot of experience working with these tools, unfortunately, but definitely should try to do it. But I know that it's possible to upload data from CC format to Tableau once I tried to do it. So which means that probably from JSON it's also possible. Yeah, I believe it's possible, but I'm not sure that it will be really convenient.
I was also commenting that we can use Power BI API. Well, that's probably something to look at. Or if you're working in one of these tools, you can also just test. There is this JSON profile functionality, and share with us. We'll be really glad to know how it works for you. There is also a question about the future plans for Evidently. So what can we say here?
Well, I believe we both can answer this question. So let me start answering from technical part of view. And I believe you can tell a lot of interesting things from the product point of view. So technically now we are preparing next release, which will fix a lot of bugs, of course. And also it will help to do sampling. And if you have huge files, you will be able to run the tool from terminal and create both dashboards and profiles on top of the smaller samples. So it will be randomized samples, which is nice for classification, probabilistic classification and data drift. It will be like continuous sampling, which is better for time series. So it will help users with bigger files try to use our tools. And well, later we are going to add some more functions. We are thinking about adding new report to analyze data earlier before you even get the nice model and you have model output, maybe something is analyzing the inputs data set. So technically that's pretty much it. And of course, we're constantly fixing and testing and adding more examples because, well, it's very early stage, right? And we have a lot of issues and sometimes it's embarrassing, but yeah, we are working on it.
Thank you for asking. Just maybe to sum up, so we're indeed early in our journey, but our goal is to build and cover all the aspects of model analytics that you might need in production or even before production when you're doing the model validation. So this is the vision, what we're creating, and it's completely built in the open, so you can go to GitHub and try it out. Also join our Discord chat and share what you think. So feel free to suggest integrations you want or something like this, because it's very important feedback for us. It will help us to prioritize what to do, Power BI or Grafana or things like this. So thanks everyone for joining. I believe we're just like finishing up the hour. So feel free to connect with us everywhere.
Thank you so much, Emeli and Elena, for the workshop. I can see by the comments, everybody really enjoyed it. And just a reminder for everybody attending the conference tomorrow, you would have received an email last night. The conference itself is not on Zoom, it's on the Hopin platform. If you didn't receive that email, check your spam folders. And if it's not in your spam folder, send us an email and let us know. But thank you, ladies, so much. We really appreciate you doing this.
Thank you so much. Thank you for having us there. We appreciate it.
Thanks, everyone.
Have a good day, everyone.
Bye-bye.
Bye-bye. Have a good day.